Good morning, everyone. Okay, so hope that all of you are doing well. So for today's lesson, I sent an announcement yesterday that the tutorial for today will be pushed to next week. Okay, because I think it's a bit too rushed to cover for me to cover the material in the morning, and then in the afternoon itself you have the tutorial. Okay, so we will push it to next week, and I think after that it should be fine. Okay, so subsequent tutorials will always have material that is already covered in the previous week. Okay, so for today, similar to last week, we will be covering a new topic. In this case, is interrupts, and at the same time, we will also review the lab manual for this week and what you're going to be doing. Okay, so as always, I will be continuously moving around between the slides, some OneNote, as well as the PDF files and the code as well. Okay, so to make sure you understand the link and the relationship between what we are looking at in terms of the theory and how we are applying it in the lab. Okay, so let's get started. Okay, because there's quite a bit to cover today. All right, so this set of slides, which is on the exception interrupts, originally when I designed these slides, okay, it was very comprehensive. Okay, if you look at the bottom here, it was actually 80 over pages. All right, because initially a lot of content regarding very in-depth discussion on the ARM processor and how it handles this. But then that would have been a bit too much, okay, information, and would have taken too much of time. And at the same time, those are things that you will cover in other modules, okay, when you are looking into computer architecture and the processor design. Okay, so all those parts I have actually removed, and then what we have now is more condensed, and I think it's more appropriate to prepare us to use interrupts meaningfully in our labs and in the project. Okay, so the overview for today would be, we'll be covering the idea of exception and interrupts. Okay, and specifically we will look into Cortex M0 plus interrupts, which is the controller processor we are using in our KL25Z. And then we will look at some timing analysis, and of course the actual design and implementation in the code. Okay, so let's start off with a quick review, okay, of what we already know of exceptions and interrupts. Okay, so the example system or the sample system we're going to be building is going to be similar to what we have done before, the RGB LED part. All right, so this is what we have used or implemented in our lab, last week's lab. And in this week's lab, we're going to be integrating this switch. Okay, so for this week's lab, you need to have soldered some of the header pins. All right, you do not need all the header pins, only one particular row. Okay, later I will discuss that. So even if you don't solder all of the header pins, at least one row you need to solder, which is the row that has the GPIO pin that we're going to be using for the switch. Okay, so that part you need to do for this week's lab. All right, so if let's say my system, okay, that I'm designing is to detect the switch event, that means whenever I press, okay, I want to detect this event. Okay, so we have gone through the configuration of the switch last week. So we see that by default, this switch is pulled up high, correct? So by default, it is a logic 1. Whenever I close this switch, I will create a short circuit path to ground. All right, so whenever I close, it goes to low. Okay, so I want to detect whenever the switch is being pressed, and when the switch is being pressed, I want to maybe toggle the LED or blink the LED or something like that. Okay, so that is the idea. Of course, a very simple system, and we can easily do it with what we already know by the polling mechanism. Okay, so polling and interrupts, this comparison is also not new to you. In fact, yes, yesterday during the EPP2 class, we went through that particular topic where we discussed polling and interrupt. Okay, so we know polling, and it is very easy, but it is very wasteful, correct? Because you are spending a lot of time checking whether an event has happened, all right, instead of doing something more meaningful. All right, and another critical issue is the scaling factor. Okay, when you have, for example, multiple events to capture, okay, it's really not practical to go through trying to poll each and every switch or every input event and see whether it has happened. Okay, and that will affect the real-time response capability of the system. So that is where the interrupts come in. Okay, so we have seen in EBP2 as well as in other modules maybe that interrupts basically help us, okay, to provide a very fast and efficient response to an event. Okay, and that is the biggest advantage that we have. And the other one is that it scales well. That means if I have more input devices that need immediate or very fast attention, I can try to map them to peripherals or inputs that can trigger an interrupt, and that can ensure the fastest response time for my for these kind of events. All right, so the whole idea is you have some background code that is running. Okay, in most cases you just have a while loop. Okay, so in your while one loop, of course, before the while one loop, you have your setup where you configure all your necessary peripherals, power, clock gating, all this stuff. Correct. And then you have a while one loop where you probably are waiting or doing some things that are sequential, or in some cases, maybe not even doing anything. Correct. If you remember the example that we looked at, the one where we do the bike performance monitoring, in that sample code, basically the while one loop does nothing but just sleep. Okay, so it just sleeps, effectively putting the processor into some low power mode, and everything is tied to interrupt. Correct, the push button is tied to interrupt, the clock is also triggered by interrupt, and so on. So when the interrupt happens, okay, you will automatically go through some hardwired response activities. These hardwired response activities are basically things like suspending your current or finishing up your current instruction, okay, saving your context onto the stack that you have, and then jumping to the interrupt service routine. So the interrupt service routine will contain some code, okay, that will be critical for the event that just happened. Okay, and once you are done, you can go back and carry on. Okay, so that is the whole idea of interrupts or exceptions. In terms of triggering mechanisms, we have seen before, okay, it can be triggered by hardware signals. Like in this uh, lab that we're going to do, we're going to use a switch to trigger it. Okay, it can also be, this hardware signal, okay, can actually come from the external device, like today, which is the switch, this week, which is the switch, or it can also be from a peripheral subsystem. Okay, so when we say peripheral subsystem, means you're talking about maybe a timer, all right, or a PWM block, or some serial interface, anything, right? So some event happen within the controller itself, and that event can also trigger an interrupt. Okay, so there are different ways in which interrupts can be triggered, and we also say it is asynchronous, so we cannot predict or know exactly when it will happen. We can say that we have a periodic timer interrupt that is happening at exactly 1 second, okay, every 1 second. Okay, but when we say we cannot exactly predict when, we do not know what we might be doing at that time when this interrupt happens. Okay, so that is of course one of the important things to remember, that we cannot pass directly pass parameters to an interrupt. So we cannot have an interrupt routine, okay, and then we pass in parameters like that. No, it doesn't work like that, correct? Because we do not know when this interrupt will be triggered. Okay, so of course, interrupts can access shared variables between itself and the main code. Okay, but of course, there are important considerations when we have that. Okay, so that we will talk about later on. In terms of the controller, the microcontroller, one of the important reasons why interrupts are critical is it actually allows us to be responsive even without an operating system. Okay, so this is what I have stressed many times, that the operating system is there, it can help us with a lot of powerful features, but in many cases you can still achieve the responsiveness that you want without an operating system. Okay, that means with the current interrupts framework that your controller provides, you may still be able to fulfill all the time requirements of the system. Okay, so that is an important point you must always remember. Okay, so in today's later on, okay, we're talking about the lab. The idea is you have a switch. Okay, when the switch is pressed, okay, so we are going to be triggering an ISR, the interrupt service routine. Okay, and inside that ISR, we're going to be updating a variable count, and at the same time, we're going to be updating the using in the main code, we're going to be using this updated variable to control the RGB LED. Okay, so the count will be a shared variable. Okay, uh, so the code that I'm going to show you later is just to demonstrate the whole framework of the interrupt. It's not necessarily fulfilling this particular binary or counting sequence. Okay, so it's just going to be blinking or not blinking. Okay, but I just want to demonstrate how the whole system comes together when you want to design your interrupt code. Okay, so let's, so just now what we just talked about things that you would have learned about earlier, okay, the general concept of interrupts and why we want them. Okay, so now let's go a bit deeper into the actual M0, the Cortex M0 Plus interrupts and understand how it is actually programmed here. Okay, so if you remember your Arduino at Mega 328, so that is a different controller with a different framework, okay, on how you program the interrupt registers, how you configure. So if I wanted a GPIO interrupt there, I wanted a timer interrupt there. So there are certain registers you need to configure, certain steps you need to follow. Okay, so every microcontroller has its own set of sort of protocol on how to configure these peripheral devices for use. And if I want interrupts, how do I configure them for interrupts? Okay, so again, microcontroller interrupts, you have things which are asynchronous and synchronous. When we say asynchronous, it's because we do not know when it will actually happen. It may not necessarily be in sync with any event that is happening. Okay, so that is why most of them are considered asynchronous interrupts. You can also have synchronous interrupts in a sense that it could be exceptions triggered because of some faulty code that you execute. Okay, so for example, could be a MPU fault, okay, memory protection unit fault, okay, or you try to do undefined or some computation that results in some exception. Okay, so these are tied to executing or execution of instructions. Okay, so we call them asynchronous exceptions. Okay, so we'll not go into that. We are going to be focusing on the asynchronous interrupt. That means those related to the internal peripherals, okay, or external devices that be connected to these port or interrupt pins. The interrupt service routine, okay, is basically the routine that is will execute in response to the event. Okay, as we saw earlier, once you finish the interrupt service routine, okay, so in your main code or in your while loop you are running, okay, and at any point of time the event happens, and when this event happens you suspend your current flow of activity, you jump to the ISR, finish up the ISR, and then you return back. So this is the sequence, okay, that we are familiar with. Now in the Cortex M0 Plus, okay, we have this peripheral block called the NVIC. Okay, so most ARM processors have this NVIC, which is basically a nested vector interrupt controller. Okay, so what does this NVIC do? This NVIC captures all the interrupt requests coming in from all the peripheral subsystems. So you can see that all the peripheral subsystems here, okay, will go through this NVIC. Okay, so when your GPIO block, your timer block, your PWM, anything triggers an interrupt, it all these interrupt requests will first go through to the NVIC, and the NVIC will then prioritize, okay, which is the most highest priority interrupt that is currently triggered, and send that interrupt request and information over to the processor. Okay, so this NVIC is like this middleman, okay, this manager that looks into all the requests coming in and decides who should be channeled over to the processor depending on priority. Okay, so we will also look at how we can configure different priority levels for the exceptions. Now, in terms of exceptions, we have 16 through 16 plus n. Okay, now let me uh, go over to your data sheet. Okay, so as I mentioned before, you should always have your data sheet at hand at all times. Okay, because we will reference that a lot. Okay, when we are looking at all the peripheral subsystems. Okay, so if you go to this page 53, okay, of your microcontroller data sheet, okay, you will see this interrupt vector table. Okay, so this interrupt vector table basically tells us the information on where the different interrupt sources are mapped to in the table. Okay, um, the first 15 or first 16 of them, 0 to 15, are what we call core interrupts. Okay, so these core interrupts are already fixed in place and cannot be altered or modified in any way. All right, and these core interrupts are having a priority in sequence. That means the starting from the first vector 0 all the way to vector 15. The all the other peripheral subsystems start from 16 onwards. Okay, so these are called the non-core vectors because these are tied to the peripheral blocks. Okay, so if you look at these non-core vectors from 16 all the way down to 47, okay, you can see that all these sources over here, okay, all these sources over here are the what you call peripheral subsystem: DMA, I2C bus, SPI, UART, comparator, timer, okay, RTC, and the last two is our port A and port D. All right, so these are all the peripheral subsystems that have interrupt capability for our microcontroller. Okay, so there's two things to this. One is the interrupt vector table number. The other one is the actual IRQ number. The IRQ number is starting from 0 all the way to 31. So there are a total of 32 different external peripheral interrupts that your system can handle. Okay, but the actual vector number is starting from 16 onwards. Okay, because the first from 0 to 15 is reserved for the core exceptions. All right, so we will come back to this table and look at a bit more on what is actually happening or how the table is actually being used, okay, by the controller when an exception occurs. Okay, so we'll come back to that in a while. Okay, so in terms of exceptions, so what we saw just now was we have 16 through 16 plus n. In this case, it is 32 32 different interrupts. All right, we have, okay, 0 to 31. Now, in terms of mode of operation, we have two modes. One is called thread mode, and the other one is called handler mode. So this switching of mode, we are not going into the in-depth here, but it's just to tell you that the processor can operate in different modes of operation depending on what kind of event is currently happening. So by default, when you go from reset, you're considered to be in thread mode. When an exception occurs, you switch to handler mode. Okay, but we are not going to go into the details of that. As well as in privilege level. In privilege level, again, it is about giving specific privileges, okay, for the software to perform certain actions at the processor itself. Okay, so when your privilege level changes, certain things you can do, certain things you cannot do, and so on. Okay, so again, those are more in depth into the actual ARM processor, which you will learn in other modules. Okay, similar to the stack pointer as well. Okay, there are two stack pointers, but we do not need to worry about them for now. Okay, so the main important information from this slide is to understand that all your peripheral subsystems go send their requests into NVIC, and NVIC will prioritize them and send the most highest priority interrupt request over to the processor for the handling to occur. Okay, so in terms of the addresses, this is what we saw just now, okay, from the data sheet. Okay, so you don't need to worry about all the numbers or hierarchy, so you don't need to memorize all these addresses or anything like that. Okay, so as long as you know that what you see here in the table, okay, I mean this is not the full table, the one in the data sheet, those peripheral subsystems are the ones that are capable of generating interrupt requests to the processor. Okay, so this is important because you want to know if you are designing a system, okay, and you're planning to use interrupt, you must see carefully that whether that particular peripheral module is able to support interrupt, okay, and is it mapped to, where is it mapped to in the vector table. Okay, so all this is important to check so you know how to write that code for that particular system you are developing. Okay, so now let's take a bit more a deeper look into how the vector table is used, okay, by the controller. So let's start with the basic one, the reset. So whenever I reset my system, okay, whenever I press the power button, I reboot the system, your code always runs, correct? The code that is loaded already inside the flash starts executing. So how does your controller know where to go, what to do whenever I press the power button and I reboot the system? Okay, so that is where the reset interrupt vector comes in. Okay, so every microcontroller has a fixed reset vector. Okay, the Arduino Uno that we studied in EPP2, the reset vector is actually address 0. Okay, for this ARM processor, the reset vector is in address 4. Okay, because 0 is reserved for the location of the stack pointer. Okay, so address 4 is used for the start or the beginning of where your code will start to execute. Okay, so when you write your code, okay, when you write your code, you compile it. Okay, so what happens when you compile your code? Okay, it has a starting point, which is your main, correct? So of course the main is the starting point that we see. In most cases there is actually some additional there may be some additional assembly language code that is executed prior to main, all right, which we do not see because it is sort of hidden to us. So whichever is the starting point, okay, the first line of code that needs to be executed has an address, correct, has an address. So let's assume that so this table is drawn such the lower address is below, higher address is on top. Okay, so let's assume that maybe the starting address of my code is here, 0xa0000000. Okay, so let's say that is the start of where my code is going to execute. Okay, so when I compile the code, what will happen is this address A0000000, this 32-bit address will be stored in this address location 4, A0000000. Okay, so what I'm storing in each of these vector table entries is the address of where that particular handler or that code is going to start running from. Okay, so when I press the reset button, my processor will come to address 4, because so these are what we call the hardwired uh, response mechanism of the system. Okay, so this is already hardwired. That means when I press the reset button, the hardwired logic will make sure that I go to address 4, take the information in address 4, which is this, and put it where? Put this into my program counter, PC. Okay, so if you have not studied program counter yet, okay, program counter is basically a register in your processor that points to the next instruction to execute. Okay, so when I take this address and I put into PC, okay, when the next clock cycle comes in, I will start to fetch this first instruction over here, this first instruction from address A000 and pass it on to my processor for executing. Okay, so I mean, if you think about it, your controller or your processor is doing the same thing again and again, correct? It's always going through the fetch, decode, execute cycle. So the first step is always that I must point to the next instruction. I must fetch that instruction and then start to decode and execute. Okay, so in order for this whole sequence to happen correctly, I must always make sure the program counter is pointing to the correct address which correspond to the next instruction that I want to execute. So that is how you are always able to boot up and run that same code correctly every time. Because every time you boot up, this same sequence happens. Your processor goes to address 4, takes the information in address 4, puts it into program counter, and then you can start executing. Okay. This same sequence is what happens with interrupts as well. Okay. So for interrupt, the vector table, what we are doing is, if you look at the vector table, all the addresses, okay, if you look at the addresses, you can see that all the addresses here differ by 4. Okay, 4044, 4846, and so on. Okay, because in each of these locations, it is the same thing. We are storing the address of where your handler is stored in memory. Okay, so when you write your handler code, okay, so your handler code, so let's say I'm doing a port B handler. Okay, so that code, you can write it anywhere, correct, in your editor. But when you compile it, this will be stored in some address. Okay, so maybe this address is 0x. Okay, so let's put it as 0000 0F00 something. Okay, some address, doesn't matter. Okay, what is important is whatever address that this is assigned to by the compiler, that address must now be stored over here. Okay, so 0x0000 0F00. Okay, so this is the address of where my code is for this port D interrupt. Okay, so that is the actual interrupt service routine, the code. Okay, but the starting point of this code, okay, this address of where it is starting from must be stored inside the vector table here. Okay, so at address 00BC, I must store this information 0F00. Okay, so the same thing happens. Okay, when the port D interrupt gets triggered, okay, I send this information to NVIC and NVIC says, okay, let's go ahead and service the port D interrupt. Then what will happen is the processor is again hardwired to go to this particular address location, which is 00BC, take the information there, which is 0F00, which is the starting address of where my interrupt service routine is going to execute, and take that and put it into my program counter. So at the next clock cycle, I will start executing the interrupt service routine. Okay, so that is basically how your vector table is used, okay, to ensure that you are able to execute the correct handler for the different interrupt requests that come in. All right, so that is the vector table and how it works. All right, those who did EBP2, we have discussed some aspect of this before. All right, so if you have forgotten, okay, you can take this as a refresher of how the vector table actually works. Okay, so besides the vector table, just now I mentioned that each of these peripherals also has the ability to configure, we have the ability to configure the priority for each of these interrupts. Okay, so to configure the priority, so we have a total of 32 interrupts, correct? 0 to 31. Okay, so these are all the interrupt requests from peripheral devices. So to configure the priority of all these devices, there are a set of 8 registers. Okay, IPR0 to IPR7. Okay, IPR0 to IPR7. And in each of these registers, okay, you configure 4 different peripherals priorities. So if we look at IPR 0, for example, okay, I can configure IRQ 0, 1, 2, and 3. Okay, if I want to configure IRQ maybe 25, okay, then I must look at intra priority register 6. Okay, so you can see that each of this chunk here is actually 8 bits. This is 8 bits, 8 bits, and so on. Okay, but within the 8-bit block, we are only looking at the upper 2 bits. Okay, the upper 2 bits to set the priority. The lower 6 bits of that 8-bit block are actually currently reserved. Okay, as I mentioned before, reserve means they are just keeping it there as a placeholder, and maybe in other future microcontrollers they will use these bits for other things. Okay, so for now we are only using 2 bits out of each 8-bit block. Okay, so for example, if I want to configure IRQ 25, okay, I want to configure IRQ 25. Okay, what I need to do is I need to go to IPR 6 and I need to configure bits 15 and 14 only. Okay, I do not need to touch the other bits. Okay, only 15 and 14 in the IPR 6 register. In terms of priority, there's only 4 priority levels. Okay, since there are only 2 bits. Okay, so it's 0, 1, 2, and 3. Where 0 is the highest priority and this is the lowest priority. Okay, now here if you look at this line here, they say it is 0, 64, 128, 192. Okay, why do we have these numbers? Because if you look at it from the 8-bit perspective, I'm only configuring the upper 2 bits, correct? So when the upper 2 bits are 0, 0, this whole 8-bit, okay, you have to remember that all the other bits, okay, are all 0. So when the upper 2 bits are 0, everything else is 0. So you get 0. When the upper 2 bits are 0, 1, if you look at it from the 8-bit perspective, you get 0, 1, 0, 0, 0, 0, 0, 0, and that is 64. Similarly, if it is 1, 0, you get 1, 0, 0, 0, 0, 0, 0, 0, so you get 1, 2, 8, and when it is 1, 1, okay, then you get 1, 9, 2. Okay, so that is why you have these 4 different levels here. Okay, so by default, okay, all of them would have some priority level, correct? So let's look at the data sheet here, okay, and see what they have mentioned. Okay, so you can see here that the IPR register, okay, you can see that the values are all 0 for the rest, but IRQ3210 is not mentioned here. Okay, so what is the default priority? Okay, so let me check. So I can't remember, but if I recall, should be 0. Okay, okay, now later let me check. Okay, or you all also can check and let everybody know. If I'm not wrong, the default priority is set as 0. Okay, okay, but let's check later. Okay, during the break time and confirm whether it is 0 or not. Okay, for the default priority level. Okay, so another important thing here. Now, in order for us to configure the priority in the code, okay, you do not need to worry about individual IPR registers, okay, and exactly putting it in the correct bits and so on. It is actually done for us very nicely through the built-in functions and macros that they have. So all you need to do is to call this function here. NVIC set priority, IRQ number, and the priority you want, either 0, 1, 2, or 3. Okay, so this one line here will actually automatically point to the correct IPR register and make sure that the correct priority level is written to the appropriate bits. Okay, so this library function NVIC set priority does it for us. Okay, so we do not need to worry about going to the appropriate IPR register and looking at the bits and so on. Okay, so later when I show you the lab code, okay, you will see how it works. Okay, similarly, you need to enable IRQ, or you can enable or disable a particular interrupt, okay, by calling this particular library function. NVIC enable IRQ and NVIC disable IRQ. Okay, so these two will allow us to either enable or disable any particular interrupt based on the interrupt number. And there's also another mechanism called set pending IRQ or clear pending IRQ. Okay, these are used to check whether there is any pending IRQ. Pending IRQ basically means that there is an interrupt, but it's not yet being serviced by the processor. That means it's still in the queue. Okay, so in most cases, it's because some other higher priority interrupt is taking over the processor at this time. Okay, so we will see how and when we need to apply some of these library functions. Okay, there's also a global interrupt. Okay, so similar to your Arduino, okay, we have SEI, CLI, and so on. In the Cortex processor, you have this register called the PriMask register, okay, which allows us to globally set, enable or disable all exceptions and interrupts. Okay, again, we do not need to directly write to the register. We can use these two functions, okay, which is to either enable IRQ or disable IRQ globally. Okay, so these are the built-in functions already provided to us to configure this masking of interrupts. Okay, prioritization, I think we just talked about it. So the priorities that we said just now only is applicable for the peripheral register, peripheral subsystems. Okay, those core exceptions, those priorities are fixed. You cannot adjust their priorities. Okay, so the reset, NMI, and so on. So these are considered fixed priorities because these are core. These peripherals are non-core exceptions, so you can sort of play around and decide what priority you want. Okay, and exceptions are prioritized, okay, to make sure that the order of execution is in the order of the priority. Okay, there is also the ability to support nested exceptions. That means if I am currently having multiple interrupts happening, how will the processor react? Okay, so if I'm in the middle of an exception and a newer higher priority interrupt uh, request is registered, then the new exception handler preempts current exception handler. Okay, so for example, if my main code is running, okay, and then I jump to a GPIO interrupt. Okay, and while I'm executing, suddenly I have a timer interrupt, and I've configured my timer to maybe priority 0, this is priority 1. So this is higher priority. So I will jump to this, finish up, then come back here. Okay, and go. So it allows you to handle nested interrupts depending on the priority level. Okay, so this is also something that can be configured in the Arduino, if you remember, but by default it is not enabled. But in our case here, it is enabled by default. Okay, so that gives us an idea of the different mechanisms for the general interrupt and exception processing. Now let's look in particular to the GPIO module, okay, and how we can actually use and configure the GPIO port to generate interrupts, okay, which is what we want to do for the switch. Okay, so again, just a quick recap. What we want to do is we want the switch, okay, to generate or trigger an interrupt service routine, which will update a variable, and we can then use that variable to control the LED or do something else. Okay, but the whole idea is the ability to use the GPIO to register the interrupt and then change some behavior. Now, the KL25Z, okay, has again a limited number of GPIO ports that are currently available in terms of bringing them out to the connectors. Okay, so there's two different parts here. Okay, one is the controller itself. Okay, the controller itself has all these pins which are multiplex, but on the board we only have some of these pins that are brought out to the connectors. All right, so we need to be mindful that, okay, for our project, okay, and while we're using this board, we need to look at what is available to on the connector pins that we can actually access. So for the port itself, port A and port D are the ones that are actually able to support interrupts. Okay, so even though you have ports A to E, okay, ports A to E, but only ports A and port D support interrupts. Okay, so that's why even if you look back at your interrupt vector table, interrupt request 30 and 31 for port A and port D, you don't have any other port uh, mapping over there at the vector table. Okay, so what we are going to be doing here is we are going to connect up the switch this way. All right, so this is what I mentioned. So for your lab this Friday, okay, or if you're going to do it earlier, so it's up to you. You need to make sure that this connector is soldered. All right, the bottom left, okay, if you have the connectors, USB connectors below. Okay, so this connector is what you're going to be using, because this is where the switch is we're going to be mapped to port D pin 6. Okay, now let's uh, let's look at this first. Okay, if I look at this connection over here, you can see that the switch is connected. Okay, so if I draw the switch, okay, one end of the switch over here is connected to ground, the other end of the switch is connected to port D, pin 6, right? This is the controller. Okay, now when I close the switch, if I close the switch, what is the logic level I will see at port D pin 6? Okay, so yes, everybody is right. Okay, when I close, I see it as 0. Okay, that is fine. But when I open, what is the logic level I see? That means when I do not press the switch, what is the logic level I will see? Okay, so some answers, some good guesses. All right, so as you can see from the hardware design, from what we see, it is not connected to any particular logic. All right, so it is considered a floating pin. Okay, it's considered a floating pin. All right, so you really do not know what voltage you will see. It's some stray voltage that particular pin might just pick up. All right, and this is dangerous. Correct, you should never configure input device and leave it open like this. Okay, you should always by default be tied to some particular logic. All right, either high or either low. Okay, so definitely if you just look at it the way it is shown here, it seems wrong. Okay, but later on we will see that actually it is fine, because internally the controller has what we call pull up and pull down capability. Okay, so later I'll come back to this and I'll show you why this configuration is fine. Okay, because we do have the ability to do internal pull up or pull down. All right, but if your controller does not have internal pull up or pull down, then you cannot do this. Okay, you should not do this. You should always make sure that there is a defined logic level at your port pins, whether it's open or closed for the switch. Okay, so I'll come back to this later when you're looking at the code and explain why this is fine. All right. So in terms of building the software, all right, what we need to do. Okay, so there are a few things we need to do. First, in the main code, we need to do some setup, correct? So we need to initialize the switch, we need to initialize LED, and initialize the interrupts. Okay, so we are going to go through that. Okay, and then of course we need to decide how we want to update LEDs or update the count inside the interrupt and inside the main code. So these are of course just application specific stuff, okay, which we will look at depending on what you're going to do. Now, what is important is making sure that variables that are shared, okay, between the main code and the ISR are declared as volatile. Okay, so volatile is a very important keyword that you need for variables that are shared. Another thing that you also need to be taking into account is that access is atomic. Okay, so we will look at both of this. Now, what is volatile? Okay, why is it important? Okay, so let me just have a quick review of volatile. If I look at this code over here, okay, so these two slides is not with you at the moment, but don't worry, when I finish all this material, I will send you the updated slides with all the notes that I've taken. Okay, so when you have a code, something like this, when you compile it and you start to execute, what happens? All right, so this X variable is declared in memory, correct? So when you compile, the compiler allocates some memory location and says, okay, this is X. Okay, and since you put a value of 0, okay, fine, I initialize to a value of 0. And inside my code over here, what do? I read from X and I update X. I read from X and update X. Okay, so inside here, what will happen is I can take this data. Okay, so if you look at this code over here, what is happening is I read from X and I update X over here and I keep doing it inside a loop. Okay, so this is the line of code where X is read and X is updated. Okay, most compilers or all compilers, what they will do is, in order to minimize memory access, prior to performing computation, you will take the value in your memory and copy it to a local register first. Okay, so why? Because memory access is always slow. It's always the weakest link. All right, whereas if I keep everything within my processor, it's very fast. Okay, so in this case, by taking a copy of my memory and putting it inside my register space within the processor, I can make my computation a lot faster. All right, then of course when it's done, I can write back later on. That is fine. Okay, so when I have a piece of code like this where there is a read, so this is where I do a read and here is where I do a write, then no problem, because I'm reading the data and I'm writing back. So I will read from memory, put it to my register, perform the computation, and after it's finished, I will do a write back to the memory. Okay, now if let's say I have a situation where my interrupt service routine is the one that is updating my variable X. Okay, if inside my main code over here, I'm only doing a read. Okay, there is no write at all. So inside this entire loop, there is no write instruction. Okay, that means there is no instruction where I say X is equals to something. There is nothing like that at all inside this while loop. Okay, the compiler, how will it behave? It will think that, okay, since there is no write instruction inside the while loop, all right, there is no necessity for me to keep on getting the updated value from the memory. The moment I read the value from X into my register, which will probably happen while I'm before at the very first instance where the loop is executed, I can just use that same register value again and again. all right, because it is looking through the code sequence and it is trying to do you a favor, right? It's trying to optimize your code and say that, okay, since there is no write to X, I don't need to waste time by continuously updating X from memory. Okay, so I just use the last write value that is already stored in my register. Okay, which is actually the right thing to do, correct? If you want to optimize for your performance. But what is unknown is that there is actually an interrupt, all right, that is updating X. So when I have an interrupt that is updating X, I'm actually writing to my X variable here in memory. But that updated value is not reflected in the main code because the main code is referencing the last captured value in the register. Okay, so that is where you have to be very careful with this kind of situation where you have shared data between ISR and volatile and your main code. Okay, so in this kind of situation, what you need to do is you need to make sure you put the volatile keyword in front. So when you put the volatile keyword in front, you are forcing the compiler to say that this variable X can be modified at any time. So as long as I'm referencing it, I cannot use the register value. I need to keep on reading the latest value from the memory. So I will force this read to happen every time I'm doing a check. Okay, so this is important. Okay, again, to make sure that you get the updated value from the interrupt. Okay, so that is where the volatile keyword comes in. Okay, so then we have the main code switches and LEDs. So all of this we will go through in a while. Okay, when we look at the code, and then we also need to make sure we set up the peripheral module to generate interrupt. Okay, so we need to make sure that the switch connected to a particular port pin, I must make sure I configure it for interrupt. I must set up the NVIC, so I must set up the priority level. I must enable all the interrupts, okay, by enable IRQ. So these are all the steps that I need to do in order to make sure my system is able to generate the interrupt when the switch is pressed. Okay, so in terms of the port module, okay, there are two registers that we need to look at. Okay, so all of the uh, port pins, so we know the port A has 32 pins, port D has 32 pins. So each of these pins can be configured to generate interrupt. So all of them can actually be mapped to your or mapped to your port module, which can then generate interrupts, which will be sent to the NVIC. Okay, so what I need to do, I need to configure the PCR register, pin control register, to make sure that the correct configuration is done to make the interrupts captured by the port module and then sent over to the NVIC. Okay, so let me, okay, so what I will do now is, I think right now it's going to be 11. We'll go for a break first. Okay, so we'll go for a 10 minutes break. Okay, and when we come back, we will look into more in depth into how to do all this configuration in the code itself directly. Okay, because I think when we look at the code, then it's easier to come back and look at the slides and see what is happening. Okay, so let's go for a break. Okay, when we come back, I will go through the actual code for this, and then you will come back to the slides and we see the relationship. All right. Okay, so let's go for a break. Now it's about 11:57. Okay, so about 10:57. 11:05. Okay, we will come back here 7 minutes time, and then let me go through the lab manual with the code. Okay, for this week. Okay, so welcome back. Okay, so let's carry on. So there are two questions here. Okay, what happens if the two interrupts with the same priority are triggered at the same time? Okay, so this depends on a few on the type of controller you are dealing with. Okay, so in our case, in our controller, there is actually a second level of inherent priority, which is the order in which the vector table is arranged. Okay, so if you look back at the vector table here. Okay, so the ordering over here, okay, of the various sub-peripherals itself has this inherent priority. That means, for example, if port A and port D both trigger at the same time, then port A and both of them are configured, let's say, to have the same IPR register level. That means, let's say, both are interrupt level, priority level 1 or priority level 2. Then port A would be registered to run first, followed by port D. Okay, so the sequence of the ordering of the peripherals here is the next level of priority if in the event where both devices are triggered at the same time and both of them are configured to be the same priority level. Okay, but again, for something like that to happen is very rare because again, when you say exact same time means both of the signal must have changed at the exact same time. All right, so it is quite rare for that to happen, but if it does happen, then you can say that we will look at the ordering here for the priority. Okay, and the other question was, would there be an overflow if too many interrupts are nested with too many variables? Yes, it can happen. Okay, so in order for you to prevent such situations of stack overflow and too many interrupts and happening, all right, so in your design, okay, you can decide whether you are going to allow nested interrupts in certain situations or not. Okay, uh, again, it comes down to, as a designer, how many subsystems have interrupts, and in what kind of situation you expect that many of them are all going to be triggering interrupt at the same time. Correct. So if you feel that you have limited amount of memory and you do not want this kind of situation, then you must control at some point of time whether I should stop the interrupts from coming in by disabling interrupts so that I can roll back first and then re-enable interrupts later on and so on. Okay, so these are possible situations that can happen. All right, and where you need to make sure that you analyze your design and take into consideration whether you want to uh, sort of control when you want to enable or temporarily disable some interrupts from happening. Correct? Or you can also think of some other mechanism instead of maybe using interrupts or some of these, then you look at the multi-threading aspect of it. Okay, so these are some of the factors you must consider when you are coming up with your design. Okay, so let's move on, okay, from where we left off here. Okay, so right now what I'm going to do is I'm going to go over to our lab manual first, okay, and then we'll come back to the slides later on. Okay, so in our lab manual for this week, okay, basically what you're going to be doing is you're going to connect up the switch to the pins. So we're going to be using port D pin 6. Okay, port D pin 6. Okay, so let me show you the connection here. Okay, so you can see over here that, okay, so let me adjust this. Okay, so you can see what's happening. Okay, so if you look at the board, all right, what is happening is the uh, pin here is your port D pin 6 and this is your ground. Port D pin 6 and ground, and that is connected to the switch. Okay, that is connected to the switch as you can see here. Now, this is the same setup that is also shown in your hardware over here. Okay, so you need to make sure you have soldered this connector, all right, and then you can connect your switch. When you are connecting your switch, these pins here also have to be soldered. Okay, so for the switch, there are two connectors. Okay, you need to solder wires onto them, so you also need to do some soldering for the switch. Okay, then you can use it. All right, so for the soldering for the switch, again, try not to keep the solder for too long. I think last batch some students melted the switch connector because they tried to put too much solder, or they put the soldering iron on it for too long. Okay, so try not to do that. Okay, so let's look at the software development. So the whole idea is you want to capture the switch event through the interrupt mechanism. Okay, so let me share with you the code sequence. Okay, and from there you will understand how to, and then we'll go back and look at the slides and the PDF file. Okay, so in our lab, okay, so first thing I have two functions. One is to initialize the switch, initialize the GPIO. Okay, so let's look at the init switch function first, all right, and better understand what is happening. Okay, so for the init switch function, so what are things we need to do? The first thing is we need to enable the clocking. All right, so these are things, like I said, I will not keep repeating. After a while, you must know that if I'm using a port module, I'm using a particular module, that clocking must be enabled. All right, so now we are still starting off, so I'm trying to emphasize this again. You need to make sure that whichever peripheral subsystem you're using, it has to be clocked. Okay, sometimes people forget this one line and they do everything else and nothing works, correct? Because there is no clock. The peripheral is not being powered up. Okay, so this part I will not go through. We already went through last week how to enable clocking based on the SCGC5 register. Okay, so if you're using port A, you enable port A. If you're using port D, you enable port D, and so on. Okay, next is the PCR register. Okay, the PCR register is the pin control register. Okay, so let's look back at that register again. Okay. Okay, so this is the PCR register. Okay, last week we also saw this register, and the PCR register, the pin control register, is for each individual pin in the port. Okay, so you have 32 bits in the port, and for each pin in the port, you can configure the behavior differently. Okay, so in our case, we are using port D pin 6, so we're going to be focusing on that particular pin and configuring that for what we want. So last week, okay, we saw the mux bits. Okay, so the mux bits, okay, were in the bit field 8, 9, and 10. And we saw that in order for me to use it as a GPIO functionality, it has to be set to 1. Okay, so that is what we saw last week, and that is the first thing over here. Okay, so port PCR mux 1 is using the macro, okay, which we saw last week, to make sure that the configuration is set to GPIO. Okay, the next, let's look at these two, PS and PE mask. Okay, port PCR, PS mask, and PE mask. So let's look at that from the data sheet. What is PS and PE? So PS and PE are both in bit 0 and bit 1 of the same register here. And if you look here, it is mentioned that the PS and PE are for the pull up or pull down. All right, so this is what I talked about earlier, that the controller's GPIO supports internal pull up or pull down. So that is why we can directly connect the switch without going through an external resistor, because we have this internal pull up or pull down configuration. Okay, so in my code, I have set both of it to 1, PS mask and PE mask. Okay, so if you're not sure, you can always go to the definition. Okay, so in the definition, you can see that I set it to a 1. This is for bit 0. This is for bit 1. Okay, so I set both the bits to 1. Okay, now coming back here. So when both of the bits are 1, what is happening here? Okay, what is happening here is I enable internal pull up or pull down. Okay, that is the pull enable. And the pull select is I can enable internal pull up or internal pull down. So in this case, the bit 0 pull select is 1. So I enable internal pull up. Okay, so I enable internal pull up. All right, so coming back over here. Okay, so what is happening here is internally to the processor, there is a pull up here now. okay, to plus VCC. All right, so this register and pull up is now internal to the controller. So the port D pin 6 by default it will now be able to read a high. Okay, when I close it will read a low. Okay, so initially it is a 1, logic 1. Okay, when I close it goes to logic 0. Okay, so that is the configuration of the PS and PE. Okay, so coming back here, so that is PS and PE. Now the last one here is port PCR IRQC with a value of 0x08. Okay, so what is IRQC? IRQC, okay, IRQC refers to the bits over here, bit 16 to 19. Okay, and if you look at these bits here, they are for the interrupt configuration. Okay, you have the ability to configure for DMA, but we're not covering that. But what we're interested in is for the interrupt based on either edge or logic. Okay, so in our case, we are using this configuration 1010, which is to generate an interrupt on falling edge, okay, which corresponds to how the switch is configured. All right, because by default it is high. When I press, it goes low. Okay, so I'm going to generate an interrupt on the falling edge of the switch. Okay, so that is the configuration here. Okay, so of course these are all the built-in macros. So if I go into the definition of this macro, you can see that it does all this shifting and masking. So I will not go through all of this again. We have gone through in detail last week how this shifting and masking all works. Okay, you can look at it. All right, but rest assured that whatever macros and definitions given here are all working fine. All right, so you can use them directly in your code, okay, to configure the individual bits in the various registers quite easily without worrying about whether it's bit 16 or bit 17 or shift by 8 or shift by 9 or anything like that. Okay, just use the all the macros and all the definitions given here, and your code is a lot easier to read and to read later on. Okay, so this configuration here basically does a few things. All right, firstly, you configure the GPIO multiplexing option. You enable pull up, internal pull up, and you also say you configure it for interrupt. Okay, now after you do all this configuration, okay, you also need to make sure that you have set the port D pin to input. Okay, so the mask I already defined, okay, as similar as last week. And in order to configure input or output, I need to write to the DDR register. So port D DDR is to configure the input for this particular bit. Okay, so those are the first few configuration. And then the last part is the NVIC part. Okay, configuring the NVIC. Okay, now for the NVIC, there are three things you need to do. First, you set priority. Okay, so when you call this set priority, okay, if you look back at the slide just now, okay, let me go back to the slide so you can see the relationship. Okay, so over here we say that in order for me to set the priority, I just call this function with the appropriate number and the priority level that I want. Okay, so that is what we saw. Now in my code, I'm going to call this function NVIC set priority port D IRQN and value of 2. Okay, so in this lab, since there are no other interrupts, whether you put 0, 1, 2, or 3, doesn't matter, all will still work. Okay, now what is port D IRQN? Where is this defined? Okay, so if you go to the definition of this, okay, let me go to the header file. So it's right at the top here. So here is where you have defined all the IRQ numbers. Okay, and you can see that port D IRQN has been defined with a value of 31, which is actually the IRQ number. Okay, so again, all of this are already given to us in the header file, so we just use the appropriate name depending on which interrupt we are writing the routine for. Okay, so over here I say that for port D IRQN, I set the priority level. Okay, clear pending IRQ. This clear pending IRQ is there as a good practice to ensure that if for some reason, maybe some other code, okay, that was written by a friend, and then you import that code in some other library or some other function, accidentally has triggered an interrupt, but you don't want to factor that in. You only want to start the interrupt from where your code is starting. Okay, so this clear pending IRQ is to make sure that if there was any IRQ that was registered in this particular port D prior to this, and you do not want to service that interrupt, okay, maybe it was done in error, you can say clear pending IRQ. So it's a good practice to follow so that you make sure that you are starting fresh without any prior pending interrupt that might have been accidentally triggered due to some other code. Okay, and the last part is you enable IRQ. Okay, so this enable IRQ is to make sure that now you're going to start registering the interrupts. Okay, so after you do that, the next step is, okay, if we look at my code here, the initialize GPIO, I'll not go through that. Is all this is just for the RGB LED, which we have already done. Okay, and over here, in my main code here, what I'm doing is I'm just trying to check whether this variable here is 1 or 0. So if it is 1, then I will keep blinking my LED. If it is 0, then I off my LED. Okay, so I just trying to just do a simple logic here. So this LED control is a shared variable that is actually updated in the IRQ handler. So this is the next thing that you must do in your code. Okay, so in your initialization of switch, you configure all the necessary subsystems, peripherals, masking, your IRQ, your NVIC, and so on. And after all of this done, you know that whenever I press the switch, what is going to happen? I'm going to jump to my interrupt handler. So I need to write the code for that. Now, inside the code for this IRQ handler, what is written here? Okay, so the first thing is you see this line here, NV clear pending IRQ. All right, the reason why I put this here is uh, more for legacy reason. Okay, if you look at many of the literature or many of online resources, they have this code here, but this is actually not necessary because the moment you jump in, the IRQ, you don't need to do this explicitly anymore. Okay, so you can actually comment off this and it will still work. All right, but I put it there just to demonstrate or to give you the idea that this is something you will see in a lot of resources as well. Okay, but it is not necessary because uh, the moment you jump into the IRQ, okay, the request has already been handled. Okay, but okay, there's another thing that you need to do. I'll talk about it in a while. So this is optional. If you take out or you keep it there, it is fine. Now, the next thing is this. So here I have two things. I am incrementing a variable. Okay. Okay. So the reason why I'm incrementing the variable is later I want to show you how the variable is going to change. Okay. So rightfully, I jump into this interrupt whenever I press the switch. So every time I jump in, I will increment my value by 1 and then I'll go. Okay. And then I toggle the LED control value. So I keep toggling between 1 and 0, and that will control the on and off of the LED. Okay, the thing that is important for you to do is this register here called the ISFR register. Okay, interrupt status flag register. Okay, this register is again 32 bits, which tells us whether the interrupt generated by any of the port pins, okay, have already been serviced. Okay, so if your bit is still set, okay, if your bit is still set, your NVIC will have the thinking that you still need to keep servicing this interrupt. Okay, so you will never be able to exit from the interrupt. All right, so if you search for this ISFR register, okay, let me show you here. Okay, interrupt status flag register. Okay, what you see is it needs to be cleared. Okay, uh, the flag remains set until a logic 1 is returned to the flag. Okay, so it basically indicates the detection of the configured interrupt. All right, so this bit in this register will automatically be set the moment an interrupt is detected. Okay, but you need to manually clear this bit in the register to tell the NVIC that you have already serviced the interrupt. Okay, if not, okay, it will always be set. Then NVIC thinks that you are still having to keep on servicing this interrupt. All right, and the way you clear it is by writing a 1 to it. Okay, so you can see here the flag remains set until a logic 1 is returned to it. So you need to write a 1 to it to sort of clear it. Okay, so that is why over here I need to clear that particular flag for that particular bit. So the bit is based on the switch position. Okay, so when you disable IRQ means you will no longer allow interrupts to come in again. Okay, that means one time come in, after that no more interrupt. This ISFR is just to clear the current request. That means once I clear, the next time I press the switch, I can still register the next interrupt. But if you disable IRQ, then subsequently you need to call enable IRQ again, then only the switch can generate interrupt. Okay, so this ISFR is just to make sure that the current request that has been registered is cleared. Okay, so that is the difference. Okay, so let me demo this to you, and you will see some interesting things that happen. Okay, let me bring up my. Okay, so let me run the code. Okay, so by default, okay, right now you can see that the LED is blinking. Okay, if I press the switch, okay, so whenever I press the switch, okay, sometimes again it triggers, and sometimes you see that it stops for a while and then it carries on blinking. So that part we know that is actually the switch debouncing issue. Okay, so because I'm not doing any particular debouncing in the code, every time I press the switch, it may register a lot of interrupts, all right, which will then uh, can cause me not to see the expected outcome. Okay, and that is the reason why I actually want to put the count variable, integer count over here. So you can see that if you look at this number here, I don't know whether I can zoom in here. Cannot. Okay, so if you look at this number here, currently let's say it's 35. Okay, if I press the switch, okay, it jumps to 39. All right, and then 58 and so it keeps jumping by a lot of numbers. Okay, but as far as the LED is concerned, every time I press, it blinks and then subsequently it will stop blinking. Okay, now let me put a breakpoint, okay, inside the interrupt itself. Okay, and then you see what happened. Okay, now if we look at the integer count now, it is 71. Okay, that means when I press, okay, the switch right now, I should be able to jump into the handler. Okay, so let me do that first. Okay, so I just press the switch and you can see that I have now stopped inside here. Okay, so now if I run, okay, you will see that from 71, you will go to 72. Okay, go to 72. All right, then if I press again one more time, okay, so again it has stopped here. Okay, it has stopped here, and now if I run again from 72, the count will go to 73. Okay, so rightfully, if I take care of the debouncing, you can see that the count is supposed to increment by one at a time. Okay, but because of the debouncing, you get a lot of false triggers with the switch, so that is why the behavior is also not exactly like what we expect. All right, but the idea is you can see that I'm able to use interrupt handler, okay, as long as I configure and do all the necessary configuration upfront. Okay, so let me show you what happens. Okay, when I remove this ISFR here. Okay, so if I do not clear this interrupt flag, okay, if I comment out this, okay, if I comment out this, what happens? Okay, okay, so if I run now, okay, it is running, and if I go and press my switch, okay, you see that my count here, integer count, keeps jumping. But that means I'm constantly stuck inside my interrupt without being able to get out. Okay, so that is why you see my LED also is frozen. Okay, because currently the last LED status that either I on or off is there, and I'm just stuck inside my IRQ handler. Okay, if I put a breakpoint here, you see I'm stuck here, and if I run, I continuously get stuck in the ISR. Okay, because the NVIC is still thinking that the port interrupt has not been serviced yet. Okay, because the flag is not clear. Okay, so you're stuck in the interrupt forever. You're not able to even go back to the main code to do anything. Okay, so that is what will happen if you forget to do this. All right, so that is why it is important that you clear the appropriate interrupt flag. Okay, once you are done with the interrupt. Okay, so let me just set this right here. Okay, so once you remove that, then it should be fine. Okay, so now if I go back and I press, the behavior is expected. Every time I press, I jump in, I do what I need to do, and then I'm able to get out. All right, so that is the demo, and that is basically what you need to sort of fulfill for this week's lab. Okay, so let's come back to the slides first, okay, on where we left off. Okay, so this is what we were talking about just now, the PCR register as well as the ISFR register. Okay, so what you need to do, okay, so the pin control register we already saw just now, where the IRQ C bits here are used to decide what kind of interrupt event you want to trigger on. Okay, so all of this code analysis we have done. Okay, so I will not go through this again. So the handler also we have gone through. Okay, so we do not need to go through this. Okay, so again, like what I've put there, the variable, setting breakpoints, okay, examining, okay, what is happening. So these are some of the things you can try in the lab to see that you are actually jumping into the ISR, you're actually changing the variable and so on. So if you press the switch and nothing happens, okay, so the first thing you should do is set the breakpoint in the ISR and confirm if when I press the switch, am I able to jump in? Okay, if you are not able to jump in, okay, then check your switch. All right, because it could be a faulty switch also. All right, So what you can do, you can just connect your multimeter, okay, across both the pins of the switch and check back. If I press it, do I create a short circuit? If I open it, is it an open circuit, and so on. Okay, so just check back whether the switch itself is okay, or maybe uh, when doing soldering or something happened and you damage the switch. All right, so you need to be able to troubleshoot, okay, to find out what sort of went wrong, okay, while you are trying to do it. Okay, in terms of timing analysis, okay, I will not go through too much here, but this few slides is just to give you the idea that, okay, so in this example, what is happening is you have a main code that is running. So in our case, our LED blinking is going on. So that is basically occupying the bulk of the time, all right? So when the interrupt is triggered, okay, through the switch, okay, what is happening is you're only executing a small portion of code. A very small amount of time is being used. Okay, so again, this is important. We have emphasized this before, that your interrupt should always be very short and very concise, so that you do not affect the activities going on in the main code. Okay, so you just take a small amount of time, do what is important, and then you're able to come back to the main code and then carry on. Okay, so of course, there is some delay, okay, in terms of the latency, and that is the amount of time you take, all right, to finish up what you are doing, jump over to the interrupt, perform the interrupt, and then come back. Okay, so that delay has an impact on how much interrupts you can actually handle. All right, so these are some of the sort of terminology that we will be looking at as well in the tutorial question as well. So for example, Fmax, we say that is the maximum interrupt frequency. Okay, that means how frequently can I have a particular interrupt happening. All right, so that ties in with how fast your CPU is running and how many clock cycles your interrupt service routine takes. Okay, so interrupt service routine takes a certain amount of time, but also there is some overhead. Okay, if you remember, when interrupt occurs, you are in the middle of doing something, right? So you need to save the state, you need to jump to your vector table, and then you need to start executing. Okay, so that is the ISR cycles. And then after that, you need to restore the state and carry on. Okay, so the maximum interrupt frequency you can have is actually given by this. All right, but of course, this is only a very simplistic way of looking at it, because you're only factoring in one interrupt. Okay, so in one interrupt, how frequently can I have it? Okay, and you also need to understand that when a processor is busy responding to interrupt, you cannot execute other code. Right, so if I am, if I come back here, if my this timing here for the ISR, instead of so short, it becomes very long. Okay, it becomes very long, then it another challenge for me to handle. All right, so in terms of utilization, okay, how much of the processor time is consumed by interrupt processing is basically given by this. Okay, the amount of clock cycles you take for the interrupt service routine plus the overhead divided by the clock frequency multiplied by the frequency of the interrupt. Okay, so don't be worried too much. In the tutorial, we will actually see how we can apply some of these numbers to get some indication on how much of overhead your interrupt is actually giving your system. All right, so I'm just putting some of these terms here so that you're familiar. When you look at the interrupt, the tutorial question, you can apply this a bit better. Okay, so program design with interrupts. Okay, I think we have gone through that enough. Okay, basically nothing much. Like what I mentioned, interrupt must be very fast, must be focused on performing the critical work, and the rest of it you put it later. Correct? Okay, you do not want your interrupt to have such a long piece of code that you cannot do what you wanted to do in the main code. Okay, now the important thing is this: sharing data safely between ISR and other threads. Okay, so the volatile is what I mentioned just now. It is critical because you want to make sure that any variable that is updated only in the ISR but is read in the main code must be reflected correctly. Okay, and the only way to enforce this is to put the volatile keyword. Now the other aspect is having data vulnerable to race conditions. Okay, so what are race conditions? Race conditions is when you have read and write operations and both having some form of timing overlap. All right. Okay, why is that so? Okay, so for example, if your main code, okay, you're doing this instruction x equals to x plus 1, correct? And in your interrupt, okay, your interrupt routine, you are doing a value of x equals to x plus 10, something like that. All right. Then in C, we write this as a single code, correct? But we must remember that technically it translates to 2 or more instructions at the assembly level, correct? Because each of these instructions will require me to load X into register, do the increment, and then write register to X. Okay, the same thing over here. So it is 3 instructions, okay, or even more. Okay, now why is this important? Because if I was in the middle of this, so if here I'm doing the load X into register, okay, and then I increment, okay, or before I increment, suddenly the interrupt comes in, and then what happens? My X get updated to a new value. Correct. That updated value of X will not be reflected here. So I will still hold on to the previous value of X, but then what will happen here is when I write back, I will write back the old updated value. Okay, so okay, take for example, X is originally 5. Okay, so when I finish this instruction here, it's supposed to become 5, supposed to increment become 6. Okay, and then I write back 6. Correct. So imagine that the interrupt happens, okay, after I do the increment here. Okay, so after I do the increment here, when I come here, this X is still reading 5, correct? It takes 5 plus 10, it gives 15. And after I finish, I'll do the write back, correct? So as far as the interrupt is concerned, I already changed the value to 15 because the interrupt happened. But then when I finish the interrupt and I come back to my main code, I will write a value of 6 into X, correct? Because both of them were trying to access this same shared variable at the same time. Okay, so these are what we call race conditions. Okay, the same variable, 2 different people trying to access at the same time. All right, and it happened to overlap. Okay, so these are also important things we must consider on how to handle it. Okay, so in OS, when we go to OS, you will see that I can handle this kind of things very easily. Okay, much more effectively. In single-threaded code, there is still ways of doing it. Okay, you can set a flag to say that the flag must be set, then I can change the value. If not, I cannot change the value and so on. So you can implement your own solution to sort of protect this data access. But with the OS, it's a lot easier to use the framework given by the OS to prevent this kind of conditions from happening. Okay, so that brings us to the end of today's lecture. So in today's lecture, basically what we covered was we covered the whole concept of interrupts and how to apply that, okay, in the context of GPIO, all right, and making sure that we are able to and the sample code that I've showed you, I think we more or less are able to make sure that we can configure the GPIO correctly, and at the same time uh, capture the input and jump to the ISR to do the processing. Okay, in the lab, if things are not so smooth, like I mentioned before, you must develop a strategy of how to troubleshoot. Okay, check your code first, check whether all the necessary what do you call that definitions and configurations are done. Okay, the power control, clock gating, input output, okay, the interrupt configuration, pull up, and so on. So check all of these configuration. Then if all the software part seems correct, check on the hardware. Okay, hook up oscilloscope to the switch and check whether is it really changing when I press the switch. Okay, if I hook up oscilloscope and your signal does not change, then something is wrong. Correct? So something is wrong, so you need to figure out what is wrong. Is it the switch itself is the issue, the wire is broken, or your soldering came out or something? Okay, so a lot of things can potentially be the issue if things are not working. So please check on that. Okay, so before we go, let me do a short poll here just to make sure that everybody is okay with what we have done so far. Okay, so I hope all of you have your data sheet with you. Okay, if you don't have your data sheet, please open up your data sheet now. Okay, and let's do this simple poll just to make sure that we have uh, a clear understanding of some of the basic programming concepts we have covered. Okay, so basically two lines of code. Two questions here, both involving some coding. So you need to look back at your data sheet and be clear on what we are trying to do here. Okay, yeah, sorry, here. Okay, so 1000, the last bit, each bit is 4 bits. I mean, each hexadecimal is 4 bits, so 0 to 3, 4 to 7, 8 to 11, and the 1 there is 12 to 15, correct? So 12 to 15, since it's hex 1 is 0001, so bit 12 is 1. So since bit 12 is 1, if you look back at your data sheet, bit 12 is referencing port D. Okay, so port D is being powered up with that line of code there. Okay, so for this question, the correct answer is enable power for port D. Okay, and most of you got that right. Okay, so for question 2, okay, so this is the code here, hex defined mask. Okay, so for the code for the mask, it is no change, is what we are used to, and basically we are taking a mask of bit 6, correct, and we are writing to port D, but we're writing to port D DDR register, which is a data direction register. Okay, and we are writing the complement of mask 6. Okay, so if I say mask 6, that means bit 6, so 0, 1, 2, 3, 4, 5, 6. Bit 6 would be a 1, the rest would be a 0, correct? Okay, but when I do a complement of it, when I do a complement of mask 6, then what happens is the reverse, correct? So this one will become 0, okay, and the rest will become 1. Okay, and I'm doing a AND operation. So when I do an AND with a 0, what happens? That bit will become 0. Okay, so for a DDR register, when the bit becomes 0, that is equivalent to making it a input pin. Okay, that is equivalent to making it a input pin. Okay, so that is basically those are the answers for this short quiz here. Okay, so I hope that gives you a clear idea of how to look at your registers and your bit masking and so on. Okay, so for this week's lab, as before, you do not need to go to the lab if you want to work remotely. Just make sure that you have soldered the pins, okay, at least for that one part of your board, so that you can connect your switch. All right, and then you should be able to run the lab manual. Okay, so that's all I have. Any questions you can ask me. All right, if not, I will see you all next week. Thank you very much.